Hi and welcome back. Today we're going to be looking at salt hydrolysis and how this relates to pH curves and indicators. Some of this will be revision about things that we've talked about before, so let's get started. So just a couple of reminders on what we're talking about in terms of acidity. We need to remember that the concentration of H3O plus ions in solution is what we're referring to when we talk about acidity. That this is measured using a logarithmic scale that we refer to as the pH scale, with each step being a times 10 difference in concentration. So as we go higher in pH, our concentration of H3O plus decreases by a factor of 10. If we go lower in pH, then our H3O plus concentration is increasing by a factor of 10. We can use the Henderson-Hasselbalch equation, which is the pH is equal to the negative log to the of the concentration of H3O plus, and this is measured in moles per decimeter cubed. That neutral solutions are defined when the hydronium ion concentration is equal to the hydroxide ion concentration. That at 25 degrees C, this means the pH will be 7, but as we learned in one of the recent videos, if we change temperature, then the pH changes. For acidic solutions, we can state that the hydronium ion concentration is higher than the hydroxide ion concentration, so therefore the pH will be less than 7. And for basic solutions, the hydronium ion concentration is of course less than the hydroxide ion concentration, with a pH greater than 7. So with all this in mind, we need to start thinking about what happens when we have salt hydrolysis, or the reaction of a salt with water. In a neutralization reaction at the equivalence point, we will have a salt formed by the reaction that's going on in solution. So if we were to look at the neutralization of sodium hydroxide with HCl, then at the equivalence point we will have NaCl present plus H2O. So this salt here is what we're looking at in terms of salt hydrolysis. The pH of the solution at the equivalence point is going to be determined by the acidic or basic nature of this salt. So the key relationship that we're looking at here is that the pH of the salt solution will be equal to the pH of the equivalence point. Remembering that for a weak acid, it will have a strong conjugate base, and a strong acid will have a weak conjugate base, and the true is conversely true for our basic solutions. So if we look at the pH of salts, with the reaction of sodium hydroxide and HCl, this is a strong base, strong acid. In aqueous solution, neither sodium or chloride will act as Bronsted-Lowry acids or bases, so they do not affect the H3O plus concentration. It is important to note that in this case we are talking Bronsted-Lowry. So when they're dissolved, they don't alter the pH, and the equivalence point will have a pH of 7. When we have ammonia and HCl, so a strong acid and a weak base, as we saw before, the chloride is going to have no acid or base properties. However, NH4+, which is the conjugate acid of the weak base ammonia, does actually have an acid property. So it can react with water, undergo hydrolysis, now acting as an acid, generating H3O+ and ammonia. This is going to generate H3O+, so it's going to drive up the concentration of H3O+ in solution, producing a pH that will be less than 7. In fact, in this titration, we would see a pH being just less than 6, at around 5.5 for our equivalence point, being shifted away from 7 towards the stronger of the two here, which in this case was the acid. And this is because of the generation of the NH4+, which is an acidic salt. If we look conversely at the strong base weak acid with ethanoic acid, ethanoate is a weak base and will react with water undergoing hydrolysis to produce hydroxide ions. This means that the equivalence point will be pushed to above 7. In fact, in this situation, it will have a pH of 9. When we have a weak acid and a weak base, both the cation, the ammonium ion in this case, where we're reacting ammonia with ethanoic acid and the ethanoate ion have acid and base properties. In this case, the pH of the salt solution is determined by the relative strength of each ion. We need to look at the Ka of the cation and the Kb of the anion and determine which would be greater. So if the Ka is greater than the Kb, then the acid wins out and the solution will be slightly acidic. If the Ka is less than the Kb, then the solution is basic. If they are roughly equal, then the solution is going to be neutral. So in this case, you're going to need to refer to your data booklet to compare the Ka and Kb values to determine where the equivalence point would sit. This is of course important because we need to know where the equivalence points are in order to be able to determine what would be the best indicator to use for a titration. So if we look at a worked example of what a question might look like, we're asked to determine whether the solution of the salt of NH4CN will be acidic, neutral, or basic. In this case, we have the ammonium ion and the cyanide anion. So we need to go to the data booklet to find the Ka of the ammonium ion and the Kb of the cyanide anion. So then we can compare them. If the Ka is greater, then it's going to be acidic. If the Kb is greater, then it's going to be basic. We can also determine the Ka of the conjugate acid by using this Ka-Kb equals Kw if not all of them are provided. So let's have a look. In this case, we are told that we can't find the Ka of the ammonium cation, so we're going to rearrange to have Ka is equal to Kw over Kb. The Kb is coming from our data booklet for the cyanide anion, and then we will determine that this is 5.56 times 10 to the negative 10. We can then work out the Kb. Okay, so in the same way, compare 1.66 times 10 to the negative 5 with 5.56 times 10 to the negative 10. We can see here that the Ka value for the ammonium ion is less than the Kb for the cyanide ion, so the solution will be basic overall. Another thing to consider now that we've looked at transition metal complexes and hydrated complex of metal ions is the hydrolysis when we're talking about a highly charged metal ion. When a salt that contains a small highly charged metal ion such as aluminium is dissolved in water, these solutions are going to be significantly acidic. Okay, and this is due to the acid-base properties, as we saw with the Lewis acid-base properties of transition metal complexes. Cations from group 1 are typically heavier and do not have a large enough charge density to attract water in the way that we see the aluminium and the iron doing in these complexes. Okay, so we don't see hydrated complexes forming with these metals typically. Lighter group 2 metals such as magnesium and group 3 transition metals will lower the pH of a solution overall though, but they have less effect than the effect we see with aluminium and iron, particularly with the 3+ charge states. So essentially what we're saying is that salts with small highly charged metal ions will form acidic solutions. This is because their high charge density will attract water and form a hydrated complex. The hydrated complex itself is a weak acid. Because the high charge on the metal will polarize those water ligands even further, the water ligands in that complex can actually donate hydrogens to water molecules in the surrounding solution. So this means that complexes of highly charged ions such as aluminium, so aluminium NO3 here, can hydrate to form a hydrated aluminium complex, which then reacts with water in an acid-base situation generating H3O+. The Ka for this is 1 × 10⁻⁵ moles per decimeter cubed. We can see with iron, the FeH2O6, so the hexahydrated iron complex, when in solution, will also produce a H3O+ with a Ka of 6 × 10⁻⁵. So the Ka of this is significantly higher. So essentially what we're looking at is that in order to determine the pH of the solution, we need to look at the ligands in the case of a transition metal complex. We need to consider whether it's a strong acid with a weak base or a strong base with a weak acid and what the resultant conjugate acid and base will be. Then, once we've established the situation that we have, we can determine what the pH will be at the equivalence point due to the acidic or basic nature of the salts formed. If the cation is a metal ion with a high charge density, then the hydrolysis occurs. And this is just showing that we talked about briefly in terms of the octahedral complex that we see being formed here and the water molecules that are around this complex. The liganded water molecules can actually lose a hydrogen, donating that proton to solution, and in this case, generating H3O+. It does affect the charge on the overall molecule because you will have lost H+. So there are some questions that you can try in the textbook to clarify this, particularly predicting what the pH will be of the equivalence point, because we'll expand on that to be able to select indicators for analysis in the next video.